So the topic of today will be piezoelectricity. And piezoelectricity, I would say, is a very interesting physical phenomenon and is used heavily in a lot of sensors and actuators. And therefore, we will, in a first part, will discuss just in this sense the material equation. So how we get the coupling between the electric, or better say electrostatic field, because it is actually really the electrostatic field and the mechanical field in this sense. And then we will go on to look how we get the governing equation, because on the one side we already have discussed here the mechanical partial differential equation, and we clearly also have discussed the partial differential equation for the electrostatic case, and we will see actually we will have some extended constitutive equation describing the coupling between the electric quantities, which will be the electric displacement D, as we just have seen in the exercises, and the electric field E. And on the other hand, it will be the mechanical stress sigma and the mechanical strain S. And then we will come up to a coupled system of partial differential equation, which will be a system for the mechanical displacement and the scalar electric potential, which we will then formulate within the finite element method, do the discretization, and look to some modeling of piezoelectric systems. So actually it was discovered in 1880 by Jacques and Pierre Curie, and it is the coupling between the electrostatic, and that makes it so important because, as we know, in the electrostatic field we apply a voltage and we immediately have an electric field. And that means that we will have for such sensors and actuators a high dynamic, and the response will be immediately, and the only delay we will have are the inertia forces, the inertia part we have within the mechanical field, so the masses we have in the structures. As you know, it is used in a lot of different devices like printer heads or servo drives. We also use it for active vibration control, so active vibration damper. A very interesting application is for injection actuators, especially used for a lot of automotive applications. We also have it in sports in order to actively damp out vibrations. And the very prominent one is the so-called surface acoustic wave device. We use their filters, and that is quite interesting because those filters you have, for example, within your mobile phone, because the electronic filtering would be too slow. Very interesting. So we are faster when we use the piezoelectric effect. You see such finger electrodes, and they have a special spacing, and when you put the electric signal to it, you will generate a surface wave. The surface wave will travel along the substrate, and with the further finger electrodes you can pick up this wave again as an electrical signal. So we have the direct and the inverse piezoelectric effect, which means we can use it for actuators as well as sensors. And due to the special structure, you can filter out special frequencies in this sense, and then can use this as a very fast filter systems for your mobile phone, but also for a lot of other devices and televisions and so on. Okay, so I just have a problem currently. I'm looking for it. Okay. Okay, so what are the materials which have this piezoelectric effect? We have single crystals. The most prominent one is quartz, so SiO2. We know it is an isolator. We have no free electric charges, but we have a dipole structure. So on the unit cell, which we will see shortly, the positive and negative center of positive and negative charges will not be at the same location, and that gives us then a dipole structure, a classical dipole structure we know from electrodynamics. The most prominent materials are so-called ceramics, ferroelectric ceramics, and there the two main materials used for actuators is barium titanate and lead zirconate titanate, and that is the most prominent one. We call it also PCT, and so this one here, and it is technical as written here, most prominent. And why most prominent? Because they have a high coupling. I just write it here, coupling factor, which means you can convert with a high efficiency electrical energy into mechanical energy and vice versa. So it is a special material which has to be polarized once, which means we put on such a material electrodes and then apply a large electrical field, so a high voltage to this structure in order to polarize it. And the polarization process at the end means that all the dipole structures will somehow orient according to this external electric field. This we will also discuss in detail. And we just have such a polarization below the Curie temperature, which is about 250 to 300 for PCT, as well as the barium titanate. And last but not least, we also have polymers, which show up these piezoelectric effects. And these polymers mainly is used PVDF as an abbreviation. And PVDF is the main material used for sensors. So this is used for sensors because it has somehow a quite good linear behavior, although the whole piezoelectric effect is a hysteretic effect, but here the hysteresis is very small and therefore we use it for sensors, but the coupling, meaning the transfer of electric energy to mechanical energy and vice versa, is not as good as we have in ferroelectric ceramics. So at the end, it is an extreme complex material with a multi-scale structure, and there are models where you really can go down to the microscale, but at the end, when you want to apply the finite element method and you want to solve a whole actuator or sensor, you have to come up to some macroscopic description, macroscopic material model, which we will discuss. It has a crystal structure behavior. The ferroelectric domains have at the end equal polarization in the crystal lattice, which we will see in a minute. And these unit cells, as we call it, they can switch their polarization just by 90 degree or 180 degree according to energy states, and typically we have a multi-grain structure. So as shown here, that would be a unit cell of PCT, and according to the atoms we have in these unit cells, we have a spontaneous polarization, as already shown here, when we are below the Curie temperature. And this spontaneous polarization is because the center of the positive and negative charges we have here are not at the same location. That is then on already a mesoscopic scale. What we see here are so-called domains. So this here, for example, is a domain, and within this domain, all the polarization vectors of the unit cells have the same orientation. Yeah? And then you call such a subregion a domain. However, on a larger scale, we have grains, and let's see if I can get here currently. It's not, yeah. That would be the next larger scale, as you see here, this one, and that would be a grain. So in German, Korn. And on this, we see that it includes a lot of these unit cells, and already within a grain, we see that the resulting polarization vectors we have there are different. And on the macroscopic scale, then when we add up all these polarization vectors of such a material, it is 0 in the case it is not polarized. And here you just see also these crystal grains. So what I have shown here, this is just a sketch. This is a grain, and as you can see here, what you see, this is also here a grain consisting of a lot of unit cells, as you can see here. Okay, so the electric polarization in this sense is the following. Actually, from the electric characterization of such materials, it is an isolator, but an isolator which we can polarize, which means that we can align all the individual polarization down to the unit cells in the direction of the applied external electric field. And that looks like this, just a sketch here. So that would be the initial state where we have all our unit cells and even domains and so on. And there all these unit cells have a polarization showing in different direction. And when you sum them up, it is a vector. So we superimpose them. The resulting polarization will be 0. However, when we apply an electric field, as shown here, because we have here the positive charges, negative charges, then we get the alignment of all the individual polarizations inside the piezoelectric material. And when you switch off the external electric field, the polarization will remain, and we will call such materials then to be active. So after a polarization process, those materials are active. They have a remnant polarization after such a process. And if we look now on the macroscopic scale, where we can do measurements, and it is somehow easy. We have this material. Mainly you make discs out of the material, and you put on the top and on the bottom an electrode and apply a voltage. So we have such a structure here. Let's say this is our piezoelectric material, and then we put here electrodes on the top and on the bottom, and we apply here some voltage. And simply speaking, as you know, the voltage over the distance between the two electrodes is our electric field, which we have along this axis here. And how can you measure the polarization? Well, as you know, the polarization is directly proportional to the dielectric displacement and the electric field. So we can also write simply that D is our epsilon 0 E plus P. And we have the very important law of Gauss that the closed surface integral of D in scalar product D gamma. Okay, so let's put this away. So that should be D in D gamma is equal to the total charges. So when we do this closed surface integral over one of the electrodes we have there, then we get the total charges out of it. The charges are from the electrodes. It cannot be from our polarized piezoelectric material because there we have no free charges. But you see, in order to have such a measurement setup where you can measure the voltage and you can measure the charges, you can make such diagrams as shown here. And when you look at this diagram, well, you see that it is quite interesting. We have a very large hysteresis. Actually, I should perhaps first put it here. This is here the zero axis. And what actually happens at the beginning is the following, that here we have a no resulting polarization, and then we apply the electric field to it, and along a so-called Virgin curve, so it is very similar as we have it in electromagnetics, we get here such a polarization over the electric field. And then when you reduce your external electric field, you go back, as we have seen there, we go back then along such a line, for example, and we end up in this point when the external electric field is set to zero. And there you see that we have this remaining polarization, which is then mainly called as PR, R for remanent. And that means our material is active. And then very similar as for magnetic materials, ferromagnetic materials, also these ferroelectric materials have exactly this behavior, that when you again apply electric field in the opposite direction, that it needs some electric field until this polarization gets to zero, and you can polarize it into the other direction. So all the individual polarization vectors of the unit cells will turn by 180 degrees to show in the opposite direction. Okay, so clearly this is a very complicated material parameter, material behavior, and it needs to be modeled by so-called hysteresis operators. However, we will just try here and set up a material model for the linearized case, and the linearized case is shown as here, that is this green line here we have. So as I have told you, when it is polarized, actually we are within this point here, and then we assume that the excitation for this material is just for small electric fields, and we can linearize it by this green line. On the other hand, we also have the mechanical behavior. So you see on the left side here the electric field, and on this axis the mechanical strain. And as you can see here, we speak here from very small strains. Anyway, what happens at the beginning, I should also show you. So at the beginning, it is following when it is depolarized. We start here, nothing happens. Sorry. So nothing happens. So we go along this line, and then after some value of the electric field, the strain starts to rise, and that is the virgin curve for the strain, which is going perhaps up to this point here. And when you reduce again the electric field, then perhaps you go back along such a line, and you end up in this point with a remanent mechanical strain. So you will also have a remanent mechanical strain. And you see, when you then again apply the electric field in opposite direction and go on, you get this so-called butterfly curve. And when you just apply the so-called unipolar cycle, which means you just apply positive electric fields to it, then you have such a behavior which is shown in this region here, according this small hysteresis you have there. Okay, so what is behind all this? Actually, behind all this is the following, that we have to look at the energy state, and for this we have to look at all the involved energies. And when you investigate the chip's free energy, then you see that the change of it is according to a change in heat energy, a change in mechanical energy, and a change in the electric energy. We know the electric energy or change is the scalar product between D and the increment of the electric field. Mechanical energy is strain and change of this mechanical stress, and the heat energy is the entropy S and the change in the temperature. This term we will mainly neglect in our case. Yeah, I just have it here to have the full chip's free energy written down. In index notation, you see it is just like this. And now when you do the following, you do the derivatives of this, the partial derivatives of this chip's free energy with respect to temperature, stress, and electric field, we get up to our material behaviors we have there. Summarized, it is on this side. So when there is a change in the entropy, then you have this relation as shown here, where the derivative is the heat capacity. You have here the piezocaloric effect, and you have the electrocaloric effect. So again, this is just to have it complete. For our case, it will not be of great relevance. Then we have the relation between the mechanical strain and the mechanical stress, as well as the electric field and temperature differences. This would give the thermal expansion. Here we would get the elastic compliances, or the inverse, it would be the elastic moduli, and we get here the piezoelectricity, as we can see here, that we get the mechanical strain due to some electric field. And for the last line, we have the pyroelectricity, we have the piezoelectricity again, and we have the electric permittivity, which we have in standard dielectric materials. So what will be of interest for us is that we have a constant temperature, so we will not consider any temperature changes, and in such a case it will be these two equations with these terms here, where we include here the piezoelectricity, where we have here the symmetries, which we will see shortly, and we have our standard Hooke's law, which is actually this one, the change of the strains with respect to the stresses, which give us the elastic compliance, and the change of the dielectric displacement with respect to the electric field, which gives us the permittivity. Okay, so now letting the temperature to be constant, we come up to this notation here already written with our tensors, with our material tensors. And you can see here the following. I just show you. This would be our standard Hooke's law. Yeah, so that would be Hooke's law. But in addition to Hooke's law, and that is now the important part, is we have in addition a term here, and this term is here proportional to the electric field. So we get also a mechanical strain S due to this piezoelectric effect when we apply an electric field E to this piezoelectric material. On the other hand, we also have here our standard dielectric material, where we have in this case here that the displacement is equal to our permittivities scaled by the electric field, our standard material law, constitutive law in electrostatics for dielectric materials. But in addition, we get here also that when we have some mechanical stresses, that due to the mechanical stresses, we can change the dielectric displacement within our material. And then this makes a so-called extended Hooke's law. We can also say an extended dielectric constitutive equation coupling the mechanical quantities, mechanical stress and strain, to the electric quantities, electric field E and electric displacement D. Okay, what is perhaps also important to say is the following. You have here some exponents. I just show them. You have here this E, you have here a sigma, and you have here a E. That means when you want to measure now the compliance tensor S, then you have to apply a constant electric field. Does anybody know how to apply a constant electric field? Since we have here coupling equation, whenever the mechanical state changes, also the electric state will change. Do you have an idea how we could achieve this? A constant electric field. It is a simple answer.
Having a constant potential?
What is a constant potential? Let's say any value. What is the simplest?
Let's say a constant potential difference. Let's say 10 volt and 0 volt.
No, then you would also have an electric field because, but you have to keep it constant. That's not easy to keep it constant because, when you want to get the relation between strain and stresses, you make experiments where you apply strong forces or you increase the force acting on your sample in order to get the relation between stress and strain. So it's not easy to keep it constant. You need the controller somehow, but not easy. You have to measure also the electric field. What would be the easiest value? Just say a value.
0.
Yes, great. Exactly. And that is important. That is extremely important. Perhaps we should also put it in our lab somehow to demonstrate it, because that means you shortcut the two electrodes. Yeah? If you shortcut them, the electric field is 0. And that you have to do. If you don't do it, and you let the electrodes open, the electric field is coming up due to the increasing mechanical stresses due to the forces you put on the sample. And if the electric field gets too strong, you have a crack and you can throw away your sample. So you always have to put the electric field to 0 within your experiments. Here it is easier. You see our dielectric permittivity. at constant mechanical stress. And that is easy, as we know. If it is not fixed somewhere, the sample, then no mechanical stresses can come up. So this is the important boundary conditions you have to apply in experiments when you want to measure the dielectric constants within the permittivity tensor. Then you need your sample to be free, no fixing of the sample. And when you measure the entries, the mechanical properties, so the electric modulus or compliance, then you have to shortcut the electrodes. So this is the important thing. Also here I just write thing is equal to 0. Yeah. So I write here mechanical no fixing. Yeah. You are not allowed to fix your sample. Okay. Now, what we also see here is that we need this equivalence as written here, which is coming out from the derivation of the chip's potential, as we have seen before, that when we measure the piezoelectric coupling tensor D, where the electric field has to be constant, meaning we just set it to 0, it is the same as doing a measurement where we let the mechanical stress equal to 0, and we just call this our coupling tensor D. And according to this value, if you look here, we know this is 3 by 1. It is in 3D. It is just a vector. We need here clearly a 6 by 3 matrix in order that this is working. Again, here we will use the Voigt notation, so we will not use here the mechanical stress and strain concerning as tensors of second order, because we know we just have the 6 unknowns, the 3 normal components and the 3 shear components, and we'll write it as an algebraic vector of the 6 unknowns. Okay, so we have at the end, because you can reformulate your constitutive equation, we have the so-called D form and we have the so-called E form, and they are totally equivalent. Clearly, when we do this linearization, as discussed before, so we don't consider any nonlinearity or hysteretic behavior, and you can compute out from the D form the values in the E form and vice versa, which you just find here. And you see clearly for a formulation to describe it with the partial differential equation, the E form is the most appropriate one, because then we can substitute in our mechanical equation the mechanical stresses. We know we have a relation between the strain and the displacement, and we then directly get here in the mechanical displacement. And here we clearly know we still have electrostatic field. We get in here our, sorry, I think I have used here the, so that was U, and here I think we have used V for the scalar electric potential. Yeah, and the same is for the second equation. We know that the divergence of T is equal to 0 in such a material because we have no free electric charges. And so also this equation makes sense, and we will put it into this partial differential equation where divergence of D equal to 0. On the other hand, this so-called D form makes sense when we want to do measurements and get out our material parameters, because it's easy for us to set the electric field constant. We set it to 0, so we shortcut this setup of the material with the 2 electrodes, and also setting the mechanical stress to 0, meaning we don't fix somehow the sample, can't be done without additional difficulties. Here it is more difficult because when you look at this E form, then for measuring the dielectric constants for getting the permittivity tensor, you have to set constant the mechanical strain, which is not easy. How? Well, you can fix it, but you need the fixing in such a sense that there is no mechanical strain change, which is almost impossible. And therefore, it makes sense to use here this deform and compute out the and measure the entries of all these tensors. And then by our relations as shown here, we can get the E form. Okay, so in this sense, we will use now, since we are interested in a coupled system of partial differential equation, we will use this E form here now for our derivation. Now, just to have some insight, we have not fully populated matrices as you can see here. We actually, it is the so-called transversal isotropic case. So within the plane, you have an isotropic material, and out of the plane is the direction of the polarization. We then will have different values, which means if we look now here at the mechanical tensor, then you can see here we have 1, 2, 3, 4, 5 parameters to be determined by experiments. That is a quite big challenge. For our piezoelectric coupling tensor, we have 1, 2, 3 parameters to be determined. And for the permittivities here, I think you see it very prominent. We have within, let's say we have x, y, z coordinate system, let's say within the xy plane, we have isotropy, and in thickness direction, in z direction, we have done the polarization, and there we have a different permittivity. So we have two parameters to be determined to get the permittivity tensor E. Okay, so here are also some values that you see the entry of the mechanical tensor, the coupling, piezoelectric coupling tensor, and the permittivity tensor. And yeah, you also see that they are quite different concerning the absolute value, because we know this is 8.854 10 to the power of minus 12. And that shows us clearly that we have quite different values. Don't forget, this is gigapascal. Yeah, so actually this is a value proportional 10 to the power of 11. And here the values are somehow 10 to the power of minus 9. Anyway, this is not a real problem. We could also rescale the material parameters because we have a linear partial differential equation we are considering here. So a rescaling can be also done. Okay, now let's look at our governing equations we have. So as we know from computational mechanics, we have here the balance of momentum, where we have the inertia force, which is density multiplied by the acceleration. So the double point means second order time derivative of the mechanical displacement. We write it in the Voigt notation, so we have here our P operator operating on the mechanical stress plus any force densities which are coming from some electrical forces, for example. So this is this G. And we know the very important relation between strain and S and the mechanical displacement U, again with our differential operator B, it's the same differential operator. On the other hand, we know in electrostatics we have to fulfill that the curl of the electric field is 0 and that the Gauss law is fulfilled. The divergence of D within a piezoelectric material is equal to 0 because we have no free electric charges. And we automatically fulfill this equation here when we express the electric field. by minus the gradient of our scalar potential. Okay, and now you see that when we also consider our linear constitutive relation, which we just have written down and discussed, we can substitute, as shown here, this sigma by this equation here, and we can substitute here this d by this constitutive equation. And in addition, we have the relation between the electric field and the scalar potential and the mechanical displacement u and mechanical strain s, which means when we do all these substitutions, we come up to a coupled system of partial differential equation as a function of the unknowns mechanical displacement u and electric scalar potential phi. So, and that is now already written here with our test functions. So we have here u prime, the test function for the mechanical PDE, and we have phi prime, the test function for our electrostatic PDE, here already written, multiplied with the test function and integrated over the computational domain. Yeah, and as you know, we do an integration by parts, which means that instead of this term, we get here this term here, and instead of this term here after partial integration, and we now neglect any surface terms, we assume that the surface terms are 0. For simplicity, we get this term here. And now we just will substitute according to our constitutive equation, our sigma and our d here, and also use the relation between strain and mechanical displacement and the electric field E and the scalar potential. Okay, so for simplicity, as I've told you, we have used here homogeneous Neumann boundary condition, but we know how to work with also inhomogeneous Neumann boundary condition, which are standard boundary condition in computational mechanics or computational electrostatics. Okay, and that is what I have told you before, that okay, what I have told you before, that when we substitute this now with the constitutive relation and the expression for strain and electric field, we come up to this coupled system of our weak formulation. And I just want to highlight the extra terms. And as you can see here, our extra term is this term here. And you see how our scalar electric potential enters the mechanical weak formulation, because all the other terms are the standard terms of the weak formulation of computational mechanics. And we see also the weak formulation of our electric partial differential equation, where we have here this additional term. Yeah? And we see how the mechanical displacement U enters the weak formulation of the electrostatic partial differential equation. Okay, so in this sense, we have now our weak formulation for piezoelectric materials. We can extend it to more complex situations, but that is in standard the weak formulation for piezoelectricity. We can use standard nodal finite elements. So the standard elements we have used for computational mechanics as well as computational electrostatics. So we will use our basis functions and approximate the continuous displacement and the continuous scalar potential by discrete one. The same we do for the test function and we come up then to a system of ordinary differential equation. So it is the semi-discrete Galerkin formulation, as we called it, because we are still continuous in time. It's quite the same as we had in computational mechanics, as you can see here. So we have here our mechanical mass matrix, we have a mechanical damping matrix, and the mechanical stiffness matrix. And on the other hand, as you can see here, let's make it green, we have our standard stiffness matrix here for the electrostatic case. And the coupling takes place in the overall stiffness matrix as shown here. So we have this coupling matrix which tells us how the scalar potential couples into our mechanical equation, and this is just a transpose of it. So in this sense we get still a symmetric overall stiffness matrix. How the mechanical displacements here witness the unknowns bold x, so all the unknowns of the mechanical displacement in x, y, and z direction for all the finite element nodes, and these couples, as you can see here in the equation, to solve for the electric scalar potential at all the nodes. So these are our standard matrices, and the additional matrix we get is the coupling matrix, which, as you can see here, computes according to this equation here, where we have here the B operator operating here. That is, yeah. So this is not correct. Sorry, these are clearly, as we know, also our basis functions in J, clearly. Yeah. And here we have the gradient of the basis function, and here we have the B operator operating on the basis function, and in between we clearly have our coupling, our piezoelectric coupling tensor. Okay, so we now also know how to compute these coupling matrices, and the last point would be the time discretization, but that we also have already discussed. We will do the same approach as we had in computational mechanics and apply the Newmark scheme for the time discretization. Okay, so perhaps I write it also here. This sense that we will apply here the Newmark scheme, as we know, which is a special finite difference approach for the time discretization. In order to come up to an algebraic system of equation, we have to solve for each time step. So what are all the modeling assumptions we have done? So it is clear that we have just small strains. We do linear computational mechanics. We have approximated the complex material behavior by the linear piezoelectric constitutive equation relating the mechanical quantities to the electric quantities by constant material tensors. We assume that clearly the whole material has been perfectly polarized. We also assume that the resistance here is zero within the electrodes. So again, actually, the model will be in the sense that we will neglect in the geometric modeling the electrodes. So if this is the piezoelectric materials, then we will just consider here the electrodes collecting all the nodes at the surface of the material and apply there, for example, a scalar electric potential different from zero, and on the bottom a scalar electric potential being zero, to get here then really voltage between the two electrodes. But the electrodes are so thin compared to the thickness of piezoelectric structures that we do not model here the electrodes itself. That is also the approach we do mostly when computing capacitances in electrostatic computation. Okay, very similar as we have it for computational mechanics, we can clearly do here the following. We can apply here a static analysis. So we neglect the inertia forces and any damping, and then we have just a static case. We can do a harmonic analysis if the excitation is by a harmonic signal, a cosine or sine excitation. If we are interested in not only the steady state case, which we get out in the harmonic analysis, we are interested in a transient case where we have any excitation, then as a function of time, then we do a transient analysis, so we have to do the time stepping. And clearly also of interest are the so-called eigenvalue analysis in this sense, because with the eigenvalue analysis, you can also find out at which mechanical modes you really have a coupling to the electric field, and at which mechanical modes there is no coupling to the electric field, which is important when you design any piezoelectric actuator or sensor. Concerning the boundary conditions, well, we can have the standard mechanical boundary conditions. As we already know, we can fix, for example, a piezoelectric structure at some surface so that no mechanical displacement can occur, or we can apply surface traction or any surface pressure load. We assume zero resistance in the electrodes, so perfectly conducting by applying just on the top and bottom layer constant electric potentials. We can also connect it to any electric network and solve then a coupled network field problem. And a very important part will be also to compute, as it's always the case for us in electrical engineering, to compute the electric impedance, which is simply the voltage over the current. Here it is just important when you compute the current and then transform it in the frequency domain to get E hat. Here we have the current as a function of time. We know it is the time derivative of the electric charges. And that is nothing else as doing the surface integration over the time derivative, as we have here, of the dielectric displacement in normal direction. And what is important here is that we don't forget that D is computed out as a function of the mechanical displacement and the scalar electric potential, and not only of the scalar electric potential according to our constitutive equation. Yeah, and simply speaking, in the frequency domain, when we just transform it in the frequency domain, it is the total charges are scaled with j omega, and we just have to integrate over the surface the dielectric displacement, which is a function, again important, from the mechanical displacement as well as clearly from the electric scalar potential. Yeah, what makes it sometimes difficult is if you have a complex structure and you somehow at any angle put there the material, put there your piezoelectric actuator or sensor. You have to rotate somehow your material tensors, which is shown here, because you have to know in which direction your material has been polarized. So let's assume you have a simple disk, and you have a polarization as shown here in the thickness direction, but then you put it onto any device and it is not aligned towards the Cartesian coordinate system, but it is somehow rotated. Then in order to get correct values out, you also have to rotate your material tensor. So this is some additional task you have to do, which is provided also within our program CFS++. So within the XML file, you can apply there the rotation angles alpha, beta, and gamma as shown in this graph here. These are the so-called cardan angles, and then you do a correct computation. If you just investigate in a piezoelectric actuator or sensor itself, it will be never a problem. But if it is mounted somewhere on a structure and this is not aligned according to the polarization direction, you have to apply such rotations. Okay, so that was the overview about the modeling of piezoelectric devices. In a lot of cases, you can apply such an approach. I have shown you with this linearization, but don't forget, actually, we have a hysteretic behavior. So next time I will show you some approaches where you really can model your device according to this hysteretic behavior we have there to see how such advanced material models are working and how you can implement it in a finite element program. However, in practice, mostly you can say I'm within some working point and apply this simplified linearized model. Okay. So in this sense,